All right. Here we go. So, for these formulas, okay, so average rate of change, that's the same thing as the slope formula. So, slope formula. Okay, now, if you remember, like way later on in Unit 5, there's average value and average rate of change. They all kind of go together. So rate of change, if you think about the word change, you're going to be doing like differences. You know what I mean? So if that helps with the verbiage or whatever to help you remember which one it is. But this is just average rate of change. You just find the slope between them. This one is also the same formula, just like a weird way to do it. It's technically this, so it's the same thing where they're doing like y2 minus y1 and then x2 minus x1, but like why do the a's? Because they just cancel out, so they just put it all over h. Okay. A normal line, I haven't seen this on an AP test. I've seen them on the older ones, but I'm just going to show it to you. I don't even show AB normal line. It's not that hard, but I don't even talk about it. But since everyone's going to get 5s on the AB portion, we're just going to, make sure we have everything covered. But they might throw that at you, but it's basically perpendicular to the point of tangency. So you basically find the slope and do opposite reciprocal. So it's not too bad. We'll do like one thing. It doesn't take that long. So just to kind of get a vibe for what's going on with this H thing and that instantaneous rate of change, like the difference between them. If you drew a little pic, this is A, and this is like, we're going to be obnoxious about the difference between this, but like when you do a limit with that distance being H, that distance, this thing is like tiny, tiny, tiny. Okay. So essentially, like if you have your curve, what did I do here? You have your curve and then you've got a point here. This would be considered like f of A. And then you got a point here. That would be considered f of A plus H. Give me a second to write it. Okay. So an average rate of change is the slope between them. Okay. So that would be like old school rise over run. It's the same thing. Like you're still doing the slope of them here because these formulas are the same. But then when your H gets really small, that's what turns into a tangent line. So like you're essentially finding the slope. What color do I want to do? You're finding the slope between these two. Okay, so like old school, like straight up line, like that's a line right here. So you're finding the slope between them. It's just when those points get really tiny or close together, that's when you get that tangent line. So, all right, so I don't know, you want to do one? I think you've done this one. I've given you this in AB before. It's an AP question. So let F be this function. Find the average rate of change. So ready, go. Find the average rate of change. Make sure you have all the things. Because sometimes this one's worth 2 points instead of 1. Yeah.
Why write? I need to write like f of x.
Yeah, you want to write f of like where you're getting the numbers from. That's right. You just need something before it. Yeah. Oh, you guys perfect. Yeah, perfect. Good. That's what on here. You gotta have this part. Close though. Okay. So you need this. This is where this becomes 2 points. Okay. Sometimes it's 1, sometimes it's 2. It's 1 for just the answer. 2, you need to show this, especially on FRQ tests. Do you know what I'm saying? Okay. On the rest of the FRQ tests, I give a point for this. Okay. So make sure that you're showing like how you're finding the rate of change, like where you're getting the numbers from. You have to tell the grader what you're doing. Okay. So you won't forget, right? Never. Good. Never again. All right. So we didn't do Robbie because I was like, well, we did Robbie last year. We'll bring Robbie back though. We did fruit flies. Do you guys still do the fruit fly lab in bio? AP bio? No? No? Well, banana. What? Oh, interesting. Oh. The ripe banana has more starch, you know. Okay. All right. So compute the average rate of change between the points. Okay. This is another type of FRQ. And then you have to explain what it means. Okay. So that's a 2-pointer, one for finding the average rate of change, and then the next for doing the explanation. Okay. So what you're going to do is don't be the kid. It's unbelievable how many people have done this in the past that do the difference in x's on the numerator. Okay. So don't be that kid. Okay. So what you're going to do is you're going to take your y's, right? So 340 minus 150 all over. And then you're going to take your x's, subtract those. 45 minus 23. And you're going to get, I did this in my head earlier, 8.6363. Okay. Okay. So what you say is you kind of rewrite the problem in a way. So it says compute the average rate of change. So they already kind of gave it away what you're doing. Okay. So you would say the average rate of change. So that's your like fraction in. Now, like what you're finding the change in is like your y's. So you're doing slope, but what are you finding the average rate of change in? You're finding the average rate of change in the number of flies or the fly population, something like that. I just said the population, okay? And then you have to talk about the x's, okay? So like when you're talking about rate of change, you have to make sure you're talking about the numerator and denominator, okay? So the average rate of change in the population from, and then you say the days, from day, again, I'm using the unit, okay? Day 23 to day, what was it again? 45, okay? And then you can go ahead and say the answer was, and then 8.6363, and then make sure you have the unit on that. So flies per day. Oh, come on. I wanted that red. Per day. Okay, so that's how you talk about average rate of change in the context of a problem. So You're doing average rate, and then you have to talk about y's, x's, the answer with unit, and then you should be good. Good? Okay. This one, so how fast was the population growing on day 23 itself? So that we're trying to get here is finding a good approximation for the tangent line. Okay, so how fast is it growing on day 23? So what is happening here is we're basically, like, we found the slope between here, but a better approximation would be something closer, and even better would be something closer, and even better would be something closer. Okay, so what we're doing is we're finding the slope between those intervals. So for this one, we've already done, that was the 8.6363. We already found between 45 and 340. So what we're going to do now is like do the slope where this is like your x1 y1 basically. And what we're doing is we're changing the second point. So if we're going to use that next order pair, essentially what you're doing is you're finding slopes over and over again. So you're going to take the 330 minus your x or your y1 and your 40 minus your x1, and you're getting those values. So you're 150 and 23, and then you get your slope, which all this I did in my head earlier, so you don't have to. Okay, so that's this point. Okay, so we did it a little closer. Now we're going to keep going. And it's trying to get you, which I don't know if you remember this from last year, but it's trying to get you to see how, as you get closer, you're getting a better approximation for how fast the population was growing. So sometimes this is your default method because you don't, like, you're only given data, like you're only recording things. Like this is a prime example is population. There's not a function really for population. You can try to create one. We'll be doing this later, actually. This is a logarithmic curve, which we'll do later. So it's so exciting, right? But sometimes this is like all we have to try to get as best of approximations for things. So this is the kind of stuff like population we do this with. We do this with trigger warning pandemics, okay? Trying to figure out when is people getting sick the fastest. So it's definitely, where'd that come from? Useful, that's for sure, with it. And I'll bring up the pandemic stuff when we get to that value, because all that data is out there. So people have already done the math with it, which is cool. So yeah, the closest you get a better approximation. I mean, it's really faster, a lot faster growth. If you look at the curve, it's a lot steeper. Okay, so what you'll be doing is you're finding slope between, like, where do you want the tangent line to be, and then you're just taking numbers, points getting closer to it. Okay. So as far as writing an expression for a tangent line at t equals 23, okay, there's 2 ways to do it. I'm going to probably focus on the H definition just because that one's the more like used one. So essentially what we're doing is we're trying to find, that's our spot. Oh, I'm going to keep with the color actually. This is where we want that tangent line. Okay, so what we're going to do is we want that distance between the points we're using to close in on it. So that means we're going to take the limit as that distance, I'll do green, that distance approaches 0. Okay, so like this point, the distance between that is your H. Okay, so the closer it gets to it, the more it closes in, the better results it's going to be. And that point there, actually I should make that blue. That's that, they want P of T. Okay, so P of and the number 23, because you're starting at this, right, 23, and this is like your h distance away. That's like what's happening. They're not talking about it as like a specific point. They're talking about it as a different distance. So if you look at that table, this number was always whatever a point away from it. So that's where that 23 plus h comes from. It's just talking about the other point, like your y2, and then minus, and then your like OG point, aka where you want the actual tangent to be, always stayed the same. Do you see I was like 50, 50, 50 all the time? So that's like when you plug 23 into the function. Okay, so this is like your 150, that you're plugging in all the time. And this is like your, like the other y, if that makes sense. Okay, and then that's all over. Now, technically, if you did slope formula, it would be like 23 plus h minus 23, right? Like your x's and stuff, right? You minus your x's. But what I'm saying is what happens is your 23s cancel, so they usually just knock them out right away. But it's still slope formula. So if I were to rewrite it, it would be h approaches 0, p of 23 plus h minus p of 23 all over h. Okay, the other definition, okay, that's involving the slope formula itself. That one is saying like your x, instead of talking about it as h, they're talking about it as x approaches that value of 23. Okay, so that's the other way to do it. And the way you write about that one is you would say your other point is just some other x. Okay, and then it'll be x down here. And it's still slope formula. So this one looks more like y2 minus y1. And then your OG point would be still the same, p of 23 and then 23 down here. So these are the two different limit definitions for a tangent line. One's talking about like the point is like exact moving, and then the other one is h. The reason they don't use this one as much is because when you're doing algebra with it, it's a pain to try to factor to get this difference out. So h is easier to deal with when you're like doing algebra with it. So cancel. Okay, just remember this stuff. I know. Okay. All right, so this part is just painful. So for this function at x equals 1, find the slope of the tangent line, the equation of the tangent line, and then the normal line. And sketch the curve of all lines. So essentially what we're going to do is the limit definition of a derivative. You guys know that's what we're doing already. So the way you would set this up, I'm going to do the h one because I think that one's a little easier, to be honest. H, hello, like disappearing here. So then for the notation, okay, the function is called y. So I'm not going to change it to f unless I define it. So I'm going to do y. And then if you're looking at where my like point is, I'm doing this at 1. So it'd be 1 plus h minus y of 1 all over h. Okay. So if you're following it, the same thing with the fruit fly thing. It's y because it's y is the function. Instead of 23, it's 1. So that's why we're doing it that way. And then now it's just like hardcore plugging in. So you're going to do the limit as h approaches 0, and you're going to plug in this 1 plus h wherever you see an x in that equation. So you're going to get 1 plus h quantity squared minus 4 times 1 plus h. And then you got to subtract number all over h. And then you have to get y of 1. Because they didn't tell me it, did they? Gosh, dang it. I mean, it's not the worst. I'm just going to do that off to the side. So y of 1 is just plugging it in. So is that -3? I'll just write it as minus a -3 to be safe, but that's what you're doing. All right, you ready to algebra? Ready, go. Algebra, start distributing, start combining like terms. Get that h out of the denominator, that's the goal. So you're just solving the limit. No one's squaring weird, right? What'd you guys get? Yep. What'd you guys get? Yep. Perf. What'd you guys get?
Oh, it's a -4.
Yep. Yep. Nice.
What? Oh, you got
Distribute the
-2?
negative.
Oh, that's what I got. Never mind.
Okay. All right, you got -2? Cool. So again, that's the slope of the tangent line. So if you need to find the tangent line, what color you want to do? Green? Sure. So equation of the tangent line. Now it says line, tangent, but line. Like, don't be extra about it. Just write an equation of a line formula. Okay? So you're just plugging in. You're going to go y minus, and you're going to plug in like where you wanted the tangent to be. So you wanted the tangent to be at x equals 1. So you're going to be using that 1 and -3 again in there. Okay, so that'd be, you're going to plug in the -3. And then the m is your, like the tangent line you just got. So that's that -2. You're going to throw in there. And then, and then we had the 1. What I highly recommend you get in the habit of is the equation for this. Move over the 3. Okay, so change this so it's -3 minus 2 times x minus 1. That's when we get into Taylor series, which is later. This is like we're going to learn about Taylor series. This is the most basic one, is the line. Okay, so that would be the equation of the line. The normal line, again, I'm not sure if they'll put this on here, but a normal line just means it's perpendicular at that point. Okay, so you just need to find the perpendicular slope, which is the opposite reciprocal. So that'd be positive 1/2. Okay, so then when you plug that in, I just recopy the equation basically and plug in the 1/2 instead. So that would be normal. So just to get a vibe of what's going on, of what this looks like, it's ish looks like this. Okay, ish. Okay, so the tangent line is at 1 would be like just skimming it. Okay, so that'd be your tangent line at 1, -3. Okay, and then your normal line is the perpendicular to it. So the way that one is just like this with the box. So why are normal lines important? It deals with vectors. That's where force should act. So you'll get into that if you take linear algebra in college. So